But first you can list some of the formulas, which which you can say is convenient to you to memorize, but if you don't memorize it, just remember the residue is the coefficient of the 1 over z minus the c sub 0, or the location of the pole, and then figure that out later. Okay, so basically you have assume you have a pole or isolated singularity, c sub 0, and you have a annular region around it, that you have the Laurent expansion, Laurent series, so you have F, otherwise is FC, is you can write it as a sum, but you can also write it like you have a, like you can have other higher negative term, but you have a minus 1 term, a minus c sub 0, right? And then a sub 0, obviously, constant, and you can have a sub 1, and then a sub 2 are other terms, right? That's the Laurent series. So the first case, of course, the simple case, the simple pole. If you have only one term and all these coefficients are 0, or the a minus 2, a minus 3, then to find a minus 1, which should be obvious, right? Obviously, you can always go back to the general formula. That is, I mean, all the coefficients are set using the same formula. It's basically a sub n is. Remember, there's the integral of the f d dz divided by c minus d sub 0 n minus n plus 1, because a sub 0 is the function at c minus y 0. If you don't have a Laurent, you don't have negative power, then that's just the Cauchy integral formula divided by 2 pi I, right? And you need the n factorial also. You have n that actually that's this the Laurent series expansion. Yeah. Actually, you don't need 2 pi. You just need 2 pi. N factorial is coming from the derivative. So if you want to express it like the higher derivative, then you have the n factorial. But otherwise, this is the general formula. So you substitute a minus n equals to minus 1, obviously. You use that a n equals minus 1 to calculate that. That becomes just 1, right? It's basically integrating that function and divided by 2 pi I, which is how becomes circular, the logic. So obviously, sometimes you can actually do that. Then you don't actually need to use the residue theorem. But you cannot do that integration, but somehow you have a Loral series, written like that, and then you know that the lowest order term is the most negative term is -1 term. This is simple pole. Then you get a minus one, a sub minus one. Obviously, you just evaluate. You just first multiply c minus c sub 0 to get rid of this factor because you have this factor. And so you have c minus c sub 0 times that c. We'll get rid of this one. You have a minus 1 plus a 0, c minus c sub 0. That's a sub 1, c minus c 0. Second power, and so on. And so to get to a minus 1, obviously, is if you substitute c sub 0 in here, so minus c sub 0 times c sub 0, and which is tricky because now you substitute c sub 0 only in here, not if you're in here, then you're in the trouble, right? And or you can use the limit notation. Because this is singular, and the singularity is 1 over z minus c sub 0. That's supposed to be cancel this one. But in a limit sense, when you take a limit, but the right-hand side is fine. You just substitute c equals c sub 0. You kill all these terms. That's quite straightforward. Now that's just a simple pole. Now, if you have another term, so you have a minus 2 divided by c minus c 0, second power, so that gives 2 power. And obviously, to get to this one, a minus 1, now you need to multiply by square, right? Multiply by square, and then your a minus 1 is supposedly you have a minus 2 also. No, yeah, a minus 1 is a minus 0, and everything increased by 1 power, but you're a minus 2, right? Now to get a minus 1, you just substituting or taking limits, hence the c sub 0 would not get you a minus 1 because you'll kill this term also. And to avoid this, and we learned about this before, right? First, you take the derivative, right? You take enough derivative of the with respect to z, then you get rid of this factor first. Let's write this one more line, right? If you take one derivative, you get rid of this power, right? And all the power reduced by whether you get rid of this term also, because this is a constant, right? Let me take derivative. Again, take the limit. And the derivative get rid of this term, you get a minus 1. And the other is 2 times a sub 0, b minus c 0 plus, or this should be 3. After you, wait, yeah, 3, a sub 1, b sub 0, 2, plus other term, and get rid of this term already. Now you take the limit and you kill all these terms and get a minus 2. Okay, so that so now you know the general way to do it because this is just stop at a minus 2, and you actually stop at a minus n, and you have c minus c sub 0 to minus n power and so on. And somewhere you have a minus 1, a sub 0, a sub 1, and so on. So this is f, right? And you stop at this term. Then to get a minus 1, then obviously the first thing to do is to multiply enough c minus c sub 0, right? So that all these, first, this becomes a constant term, c minus c sub 0 to the power n, c, a minus n, and then you have a minus n plus 1. And that one, because of you multiply by n, this is n minus 1, n minus 1 in the denominator, so you have a c minus c sub 0 here, and then also and so on. The minus 1 term is now c minus c sub 0 to the n minus 1 term, n minus 1 power, and then a 0, and c sub 0 to the n power, and so on. Right? Now, do the same trick to get a minus 1. Then you want to get rid of all these other terms by taking derivatives, because they are at most c minus c sub 0 to the n minus 2 power. This is n minus 1 power, right? And so you take n minus 1 derivative, then you will get rid of all these other terms in front of it, right? Because they don't have enough c power to survive all the derivatives, right? And you need to do this c n minus 1 power c to the n minus 1. Right? And again, take the always limit of c tend to c sub 0. Okay. Now you get rid of all this, right? After you take the n minus 1 derivative, you get rid of that. But also, yeah, you need the factorial, because you take n minus 1 derivative, so you have an n minus 1 factorial, and you get the a minus 1, and then that one also has a n, actually it's n factorial, but that doesn't matter, because you kill all them by c tends to c sub 0, so these other terms are all 0 after you take the limit. So the formula will be a minus 1, the residue is this limit divided by n minus 1 factorial. Okay, so you get the general formula. And this general formula, if you apply back to a simple pole is just n equals to 1. So 1 minus 1 is 0. 0 factorial is defined as 1. And the 0 derivative is not taking derivative at all. And so you got c minus c sub 0, factor 1, just itself, and times the function, and take the limit. So you get back to the special case of a simple pole, and then also all the different order. Okay, so that's the way to get to the formula. Obviously, if you remember the formula, that's fine. As always, reassuring to remember the formula. But if you are not very sure about your memory, like in the exam, and unfortunately in our comprehensive exam, we don't allow the use of mathematical handbook. So So, if the question doesn't give you the formula and you're not very sure about your memory, you remember maybe n factorial or n minus 1 factorial and all that. Just remember the process, how you do it. Right? So, because the fortunate thing, we give you plenty of time. There's a time. We give you 6 hours for 3 questions. So you have 2 hours per question. So we have plenty of time to figure things out. Okay, it's not too long, right? It's all the derivation. Just do it line by line, and then try to figure out what the genuine method to get to this a minus one coefficient. That's all it is for finite order poles. And for essential singularity, you have infinite power. Obviously, that will not work because you cannot take infinite power, right? And so then you're back to either using this general expression, that basically just n minus one, which is integrate around the singularity divided by 2 pi I, which is usually not possible. Then the other method is just somehow find a inverse power expansion of f around the singularity, and that for essential singularity that would be infinite series. If you can find that, then find the coefficient of the 1 over z minus c sub 0 term. That would be the way to do it, right? And that's all the way to calculate the residue. Okay, is that clear? Any question about it? Any? All right, so not too bad. And then the textbook have some examples, and I'm not going to go through all of them because again we will have plenty of chances to use to calculate residue to as part of the steps to evaluate integrals, and we have plenty of opportunities. So just mention a few of them. The first two are simple. They are simple poles. Number three, actually, I wanted to point out this one. This is also simple pole, but then the textbook, at least my version, has a typo. I don't know what your new version, whether they corrected it or not. B square plus 4. This is number 3. This is example 1. Right. And my version has C equals to evaluate the residue at C equal 2 times e to the power I. Is it the same in your version? Are you, or everyone has the same version? This example 11.7.1, number 3. Do you have all? Is the textbook in your textbook also different? Which can you see that this is not a pole? Can you see that? This is not singular at here, right? Yeah. It's not. So sometimes books has errors. that that's the reality. So you don't trust your textbook. Don't always trust your textbook. Okay. But this is a simple error. You should easily see that because that's not a pole. And the first thing you do with respect to something more complicated in the denominator, it's best to factorize it if you can, if it is possible. And this is simple to factorize. This is equal to c by minus 2i plus 2i. Right? Can you see that? Right? Because this is a minus b times a plus b, which is a squared minus b squared. But b is 2i, so b squared would be minus 4. Minus 4. You have b squared is minus 4, but you a squared minus b squared, so minus 4 plus 4 is equal to c squared plus 4. Okay, so that's the factorization. So the poles are, those are simple poles, plus the minus 2i. Okay, and because log c is a multi-valued function, so it's true that you need to specify the phase, otherwise just 2i is not enough, right? So again, like you want to get the poles at I, which is 2i, you can say is 2 e to the I pi over 2, right? We try to evaluate that, which is equals to 2i, but this one is more specific. The phase is specific, so that the log c is the branch of log c is fixed by using this. Okay, so the residue, obviously follow the symbol pole. You multiply c minus 2i, which cancel this one. So you have becomes a limit. C tends to 2i log c equals 2i. Right. And that is you should substitute this into here, becomes log 2 plus I pi over 2, and the 2i just 4i. Right. So that's straightforward. Right? Okay. And it's okay for this one. Yes. Very straightforward. One here. The following one is form is C divided by sine squared. So this function obviously has a pole at 0, and all the zeros of sine z. And sine z has many zeros. You know that sine is oscillating on the real axis, and then they are all the zeros are actually on the real axis. They have no compact zero, right? And then all the n pi's are 0, right? And square doesn't matter. Sine z is 0, then sine square z is also 0. So you have 0 also. So 0 of sine z becomes the pole of this function. So the poles are n pi, right? Right. But because of the square, that becomes all this becomes second order poles. Because all the zero will be simple zeros. They are not, they don't have multiplicity. Just c minus n pi, right? So the textbook asks you to evaluate at pi, just pi, so at n equals to 1, and you can do that for any number. But except for c equals 0, then you kill with one factor with c in the numerator. That becomes a simple pole again. And that is what we call the removable singularity. We talked about that. I mean, that meant not not total removal. You remove one factor when you take the limit. It's still a pole, right? But then it's not a second order pole, it becomes a simple pole. But for c equals to pi, that's a second order pole, right? Then according to our formula, you multiply by c minus pi, and then multiply it by the function sine square z, and then we take the limit of z equals to pi. Right? No, I take the derivative. Yeah, don't vote. The second order. Yeah, second order. Take the second order. Yeah, I erase that. You multiply enough the factor to kill the the most negative power of this, and then take the derivative. Yeah, right. And then take the limit. All right. Right. This is the formula. You remember? Yeah. Okay. Uh, so that is you just keep doing it, and we'll take the limit later. So just take the derivative first, and see what we get. The derivative is first take the derivative of the numerator, right? Right. The numerator you have first you have derivative of this c minus pi square. The other is derivative of this one times c. Then that's 2 c minus pi times c. Yeah. Okay. And then you take the derivative of the numerator, right? A denominator minus 2, and keep the numerator, and this one sine cube of c, and then cosine of c, right? That's the derivative, right? Can you follow that? Right. I'm not writing that taking the limit. We take the limit later, right? And let's get to the common denominator. Sine cube c. Sine z times this factor. Let's see if we can simplify that. You have this factor is c minus pi, and then c minus pi plus 2z, right? Which is 3z minus pi, right? So that's this factor. 3 minus pi factor of 3 minus pi plus 2z. Okay, and then the other factor is minus 2 pi square and z. Okay, now the problem is that now you take the limit of c tends to pi, then you have a 0 at the 0 pi, but this is a cubic power, right? So and that is also sine c is 0, and this is 0, and this is not 0. So you should take strictly, then this term will be singular. So you need to find a way to combine the two. So needs a bracket. But this term is also not it's just second order in c minus pi, and z is pi, and cosine pi is -1, right? Because pi is -1, so this is also not singular. So the numerator is not doesn't have enough zero to cancel this yet. You need to combine the two terms. You need to find one way to combine the two terms. Yeah, I see minus pi. I see it will work. Right. And that is sine b c minus pi, which turns out to be just 2 pi because of pi c pi, and then the minus 2 c minus pi 0, and then c, which is pi cosine. Cosine c, that's not taking. Yeah. Okay. So after this, do this. Let's see if this is actually cancelled. This is obviously you have sine c is 0, but c minus pi is also 0 of the same order. Now the rest, see if they are the same, because it's 3c, you got 3 pi, 3 pi minus pi is 2 pi, and this is 2 pi, this is 1. So this actually cancel. So this will give you one more order, right? And now what do you do to get to the the uh, the cancellation? So you can either using the whatever they call it, we take the derivative of the numerator, and then yeah, that you do keep doing that until you get a limit. You know that it will work, right? Another way to do it is using Taylor expansion, right? Do a Taylor expansion of both the numerator and denominator, right? Which is basically the same, right? So everything you need to have c minus pi. You need to have enough c minus pi, so you can now try to take the Taylor expansion sine c with respect to pi, right? Which is sine of pi, which is 0, plus cosine at pi, which is -1, and c minus pi. Right. That's the first term, right? And let's see if we get, if we have one, if we have this first term in here, and we do the same thing for here, and you get c minus pi in here, and then supposedly you combine these two, you get another c minus pi. Hopefully you have enough to cancel all the c minus pi factor in sine cube, right? And so see if this will work. So sine pi is 0, so this is minus c minus pi. So, right, this is cosine pi is -1. Right? You all see that? The sine cube is minus of c minus pi cube, and then we'll do that the same thing for cosine pi, cosine c. Want to get rid of all these things. Cosine pi. Cosine pi is -1. And then the derivative becomes minus sine pi, which is 0. And c minus pi. And so you don't have the linear term, so you just have -1. You have the second order term, but that second order term in here multiplied by c minus pi multiplied by c minus pi to fourth order, that would become 0. So you just keep up to -1. But so now see if we have enough to go back to here. Now c minus pi. And that is minus c minus pi. Or you can take this out, another factor out. Then this becomes -1 and multiply by this one, minus bc plus pi. This becomes this one. C minus pi is out. This becomes minus 2z. But c becomes -1, we can plus 2z. And divided by the denominator, become minus c minus pi. Wait, just use that. Now see if we can cancel this minus 3 pi, minus 3c plus pi plus 2c becomes minus c plus pi, which is minus bracket c minus pi. So there's a -1 here. So the numerator is also minus c minus pi cubed. This 2 divided by that is just 1, right? Do I get 1? Yeah. Yeah, I'm lucky. So the residue is 1. Right? So if you are lucky and patient, you finally get it. So the idea is just to take the limit. And I mean, another way to do it is start with just a series expansion. See if that will help. You start with this one going into here, and try to get the inverse power of that. We can try. I mean, this is. I mean, when you get the higher order, it becomes more complicated. So this, we can see this comes in, and then sine square z. You can use this one. Because you need the inverse power of this, so you need actually higher order term. So you need to, or maybe I'll write it here. So this is square of sine. So sine pi is 0. This is Taylor expansion of sine z, right? We can actually do the Taylor expansion of sine square z, and rather than doing sine z, and see if that will actually better. So sine square sine square z at pi is 0, and the first derivative is sine pi cosine pi, which is also 0, and then c minus pi That's order zero. And then plus the, but that turns out not to be not to be easier. Yeah, that that you will see that C minus uh, yeah, I can't do it that without one more step. So two sine z cosine z, right? We take the derivative from two sine cosine square. Take a derivative of this minus sine square. And that evaluate at pi, this is 0, this is minus 1 is 1, equals 2, and divided by 2 factorial is 2, so minus 1 square. No, now you got the Laurent, this is 1. Right, you got the c minus 2 terms, and that is just a function of c, so you need to, well, you can change this to c minus pi. Say that again? Minus pi plus pi, right? But I'm wondering why the curve. Oh yeah, you need to find the a minus 1 first. Yeah, the a minus 1 is z minus pi divided by c minus pi squared, so it's 1. The coefficient of a minus 1. Yeah. This pi is the coefficient a minus 2. Yeah. Right. So, yeah. But anyway, another way to do it is like that. Well, there's a way the textbook suggests you, which is fine, maybe a little bit easier, because working with this non-zero is sometimes it's not easy. So the textbook suggests that you do basically shifting z to a new variable, change a variable. Just call c minus pi a new variable w, which work out, but um, just like just some caution when you do change a variable. This change of variable is okay. You keep the new variable proportional to this with proportionality 1. You don't want to have a multiplication factor here, and you don't want to change the sign because that would change the residue. If you change a variable in a by changing the multiplication and then changing the sign, the residue will change. So you need to be careful when you use change a variable to calculate residue. If you do that, you need to change it back. After you calculate the residue in new variable, you want to figure out what the residue in the old variable. Okay, so that is more complicated. Okay. So we spent enough time. Okay. And the essential singularity is the example is trivial. We did that before. If you want to see, we do the Taylor expansion of e to the x power. So one part e squared over 2 d6 actually. Right. So that's just a Taylor expansion of that one. Obviously, a minus 1 coefficient is just 1. At the essential singularity at c equals 0. And that is the only pole for this function, right? So, oh yeah, the textbook is minus 1, so doesn't matter. You just change the orders to minus 1. Then for this function, the singularity, the residue is minus, the other is 2. So it's not too bad. So if you actually can find another way to do the expansion, right? It's okay. So this is just some example. You should calculation residue should not be difficult when you found when you apply to do integral. Uh, Usually the integral will not be so complicated. You can find the residue. As long as you remember this, the procedure to find the residue. Is that okay?
Taking the product minus 1.
Say it again.
In e power minus 1 thing, by taking 1 as the
Oh yeah. This is just copy. So this is no, this is the tail example. This is still right. This is still right. 1. Yeah. Because the zero power is so I'm using cx is 1 plus x squared over 2. Right? This is a Taylor expansion. I substitute minus 1. X equals minus 1. Right? 1 over minus 1 over z. Then this is minus 1 over z. And this is this one. That's a minus 1. Right? I'm just using that one. Yeah.
So then if you were to take the integral of that e to the power 1 over z minus 1 over z or minus 3, it's just it's 2 pi times the sum of residues, right? And there's only one residue minus 1. So
that depends on how you put this in. Because if you are considering a real integral, obviously this one is not well defined. You have real integral exactly this function along the real axis. This will not be a well defined integral. So you have exactly a singularity along your integration path. You hit the singularity. So it depends on where you put your integral, what the function of the integral is. But if this becomes real, then this integration you integrate over 0 will not be well defined. You need to have a that we'll talk more in the next section. Different cases how you use this idea of the residue theorem. To do that, there are different cases. There are actually many cases, more cases than you can imagine. This textbook will just consider just a few most common cases, and you look at real complex variable textbook, at many more examples, many more situations you can do. But the idea is first, when you apply the next section, this is going ahead a little bit. So you look first, you study your integral first. Most likely you want to evaluate some real integral over real variable along the real axis. That's the most common case. And you want to have an idea what the integral, whether it's singular, whether it's well defined. Then before you try to use the complex integral, define some contour to try to solve this integral. So the first step is actually more important. And that will actually check your results. So if you have totally real integral defined on real axis, then you don't expect any complex result. If after all your calculations you get a complex number out, then you did something wrong somewhere along. Okay, so you need to be a little careful. All right.